In this video, we're going to determine concavity. We'll be talking about topics from 3.3. So let's go ahead and get started with that, starting with number 5 in the textbook. 3.3 number 5 says f of x is equal to a negative 3x squared. Now, I've already introduced the topic of concavity a little bit earlier when I was talking about using the second derivative test for extrema, when we were talking about extreme values and how we could use the first derivative test or second derivative test. This is where the topic of concavity is officially introduced. We're going to use the second derivative to find concavity. So here's the first derivative, and then we're going to take the derivative of that derivative to get the second derivative. We use our number line technique to say, where is this second derivative, positive or negative? Well, it's negative everywhere, from negative infinity to positive infinity. And if a region on the number line that we've drawn here for the second derivative is positive, that region, that interval is concave up. If a region is, or interval is negative, that region is concave down. So because it's negative, we're concave down from negative infinity to infinity. Let's look at another problem that's going to have some additional intervals to it. Y equals to negative x cubed plus 3x squared minus 2. My first derivative will be a negative 3x squared plus 9x. My second derivative will be negative 6x plus 9. When I set that equal to 0 to find where it changes sign, then negative 6x equals negative 9. X is equal to 3 halves. A word of warning, even though we're doing the same process to find these numbers here, do not call these numbers critical numbers. Critical numbers are related to the zeros of the first derivative, not the zeros of the second derivative. The zeros of the second derivative tell us something else. Whereas a critical number implies that it might be a turning point in the graph that is a minimum or a maximum. This is a different type of turning point in the graph that's called something else. More about that later in another video from this section. In fact, I think it's going to be the very next video we make. Yes, it will be. So hang on and we'll learn what to call these, but do not call these numbers critical numbers. They are not. So that gives me an interval from negative infinity to 3 halves and an interval from 3 halves to infinity. Something less than 3 halves, like 0. When I stick it in here, 0 plus 9 is 9, and that's positive, making this side concave up. Something bigger than 3 halves, like 2. Negative 6 times 2 is negative 12. Negative 12 plus 9 is a negative 3, which makes this side concave down. So we're concave up from negative infinity to 3 halves. Again, open intervals here. We're concave down from 3 halves to infinity. Let's go ahead and look now at number 9. Number 9 is a bit more challenging because it is f of x is equal to x squared plus 1 over x squared minus 1. And I'm going to need to consider those vertical asymptotes as places that the concavity can change as well. I'm not just interested in the zeros of the numerator of my second derivative, but also the zeros of my denominator. as places that the concavity can change. So let's go ahead and identify my numerator is x squared plus 1. My denominator is x squared minus 1. The derivative of my numerator is 2x, and the derivative of my denominator is also 2x. If I call this u over v, that makes f prime equal to u prime v minus v prime u all over v squared, which makes this 2x times x squared minus 1 minus 2x times x squared plus 1 all over x squared minus 1 quantity squared. So f prime of x is equal to 2x to the third minus 2x minus 2x to the third minus 2x over x squared minus 1 quantity squared. That gives me a negative 4x over x squared minus 1 quantity squared. I have another quotient now, so I'm going to have to use the quotient rule again. And that's going to give me u is my numerator, v is my denominator, and u prime is negative 4, and v prime is, we're going to use the chain rule here, 4x times x squared minus 1. So again, we have this rule about what the second derivative will be. And so we have u prime v minus v prime u all over v squared. I'm going to go ahead and do some factoring right away in the top to help me. I'm going to take out a negative 4, and I'm going to take out an x squared minus 1. And that leaves me with x squared minus 1 in my first term. And that leaves me with negative 4x times x is negative 4x squared. And we've taken out the x squared minus 1. Let's close that up over, and down here will be x squared minus 1 to the fourth. When I divide like bases, I subtract the exponents. This turns into f double prime of x is equal to negative 4 times x squared minus 1 minus 4x squared over x squared minus 1 to the third is a negative 4 times a negative 3x squared minus 1 over x squared minus 1 to the third. I'm going to take that negative 1 out of that factor in the top to get f double prime of x is equal to 4 times 3x squared plus 1 over x squared minus 1 quantity cubed. So what I see in the top is that there are no zeros of the top because that factor is a sum of squares. So it's never 0. There are zeros in the bottom that I'm interested in, that the denominator is equal to 0 when x is equal to plus or minus 1. So those are vertical asymptotes from my original. They're not in my domain. They're vertical asymptotes, but the concavity can shift there. So I'm going to put dashed lines there to represent that there are vertical asymptotes in the graph here. And I'm looking at f double prime here. So from negative infinity to negative 1, let's look at a number like negative 2. The top is always going to be positive. If I have a number less than negative 1, like negative 2, that would give me 4 minus 1 is a positive 3, and a positive 3 cubed is a positive. A positive divided by a positive is a positive, and this interval will be concave up. Between negative 1 and 1, I'm going to test a number like 0. Go ahead and do this on your calculator if it helps you to go ahead and put this function in and use a XY table and put in some of the numbers that I'm talking about. So I talked about negative 2. I'm going to put in 0 as a test point here. I'm going to put in 2 as a test point over here. I'm only interested in the sign, SIGN, sign of this number, not the value itself. When I stick in 0 here, though, it's positive in the top, and negative cubed is negative in the bottom. A positive divided by a negative is a negative, and this section is concave down. And then when I stick in 2, the top is positive. 4 minus 1 is a positive 3. A positive 3 cubed is positive. A positive divided by a positive is a positive, and this section is concave up. So I'll be concave up from negative infinity to negative 1, union 1 to infinity, and I'll be concave down from negative 1 to 1. That was this one. All right. That will be it for this video, and we'll come back next time and we'll start talking about finding points of inflection, and I'll probably tell you a little bit about how that's related to concavity and what those might look like on the graph. Probably draw a little picture for you or something to help you have an idea of why those are interesting points to us and why we want to find them to help us draw a graph. So come back for that next video on points of inflection. See you for the next video.